Hello, my good friends. My name is TTJ Kepsi Richard, and welcome to my online tutorials. Our discussion on numerical and computational methods will be on Gregory Newton's difference interpolation formula. When we talk of Gregory Newton's difference interpolation formula, there is two formulas to that regard. That's the forward difference formula and the backward difference formula. Before the video will end today, I will take you through how the forward difference formula came about and how the backward difference formula came about. This will be a very interesting engagement, so please be my guest. So if we have a difference table like this, where the polynomial function connecting x and y is 2 degree 3, because when we find a tail difference, we have constant. Please check out my videos on how to construct difference tables on YouTube. So you can say that this value here, that's del y naught, is equal to y1 minus y0. So that will be y1 minus y0. Then this difference here, that's del y1. It will be equal to y2 minus y1. So y2 minus y1. The same way, our del y2 will be equal to y3 minus y2. I hope you get that. So we are going to use this to develop Gregory Newton's forward difference interpolation formula. So the first one, that's del y naught, is equal to y1 minus y0. Let's make y1 the subject. So you can say our y1 will be equal to del y0 plus y0. That's bringing the y0 here. So our y1 will be equal to, now I want to factor my y0 out. So I'll have del plus 1 y0. I hope you get that. Or y1 is equal to 1 plus del y0. Please remember, when this is 1, you see that the exponent here is also 1. So take note. So having find our y1, and we know it's equal to 1 plus del in bracket y0. And the second difference, that's our del y1 is equal to y2 minus y1. Let's try to make y2 the subject. So we can say y2 is equal to y1 plus del y1. So y1 is common to them. So we can say y2 is equal to 1 plus del y1. Now what's our y1? Our y1 is 1 plus del y0. So we substitute. So we can say our y2 is equal to 1 plus del. Then in place of y0, we substitute 1 plus del y0. So our y2 will be equal to, so 1 plus del, then 1 plus del can be 1 plus del exponent 2 y0. I hope you hear that. Also, we said del y2 is equal to y3 minus y2. Let's try to make our y3 the subject. So we can say y3 will be equal to y2 plus del y2. So our y3 is equal to, y2 is common, so we factor it out. We can get 1 plus del y2. And what's our y2? Our y2 is giving us 1 plus del squared y0. So we substitute that. So we get our y3 is equal to 1 plus del. Then in place of y2, we substitute 1 plus del squared y0. So our y3 will be equal to, so 1 plus del in bracket times 1 plus del squared will be 1 plus del cube y0. I hope you get that. So when we have y1, we realize it's equal to 1 plus del, remember exponent 1 y0. And when we have y2, it's equal to 1 plus del square y0. When we have y3, it's equal to 1 plus del cube y0. Now we can conclude that if we have y4, without solving, we will get 1 plus del exponent 4 y0. Is that not it? So that will continue. So we can say when we have yn, it will be equal to 1 plus del exponent n y naught. I hope you get that. So we are going to use this to develop Gregory Newton's forward difference interpolation formula. So this can be rewritten as y subscript n is equal to y naught bracket 1 plus the exponent n. So I just interchange the position. Remember, multiplication is commutative. Now, how do we expand 1 plus the exponent n? Remember, when you are learning binomial expansion, you make 1 plus x exponent n. The expansion will be 1 plus nx plus n minus 1 all over 2 factorial x squared, then plus n minus 1, n minus 2, all over 3 factorial x cubed in that order. I hope you get that. So, when we have 1 plus del exponent n, we can say the expansion of this, that's in place of x, we substitute del or delta. So we can have 1 plus n delta, then plus n minus 1 over 2 factorial delta square, then plus n minus 1, n minus 2 all over 3 factorial delta cube plus in that order. Now, so we know the expansion of this. We substitute it in place of this and take it from there. So since we realize that the expansion of this is this, we are going to substitute. So we can say our y subscript n will be equal to y naught bracket. In place of this, we substitute that. So we get 1 plus n delta, then plus n minus 1 all over 2 factorial delta square, then plus n minus 1, n minus 2 over 3 factorial delta cube plus in the order. So when we let the y naught multiply everything, we get yn is equal to y naught plus n delta y naught, then plus n minus 1 over 2 factorial delta square y naught, then plus n minus 1, n minus 2 over 3 factorial delta cube y naught plus in the order. I hope you get that. So how we expand that? This is called Gregory Newton's forward difference interpolation formula. I hope you get that. Now the question is, how do we get y naught, delta y naught, delta square y naught, delta cube y naught? These are the values. Look at it. These values. You see that this is y naught, delta y naught, delta square y naught, delta cube y naught. So that's those values that we are going to pick when we try to apply or put this into practice. Now let's learn how Gregory Newton's backward difference interpolation formula also came about. So our next stop is to look at Gregory Newton's backward difference interpolation formula, having taken you through the forward difference interpolation formula. So this is called the backwards difference operator. That's the nabla. It's called nabla. So we can say that this nabla of y1 is this difference, this value here minus that value. So we can say nabla y1 is equal to y1 minus y0. The same way, what you want to find is that's nabla y2. It will be equal to y2 minus y1. The same way, if we need the nabla y3, it will be equal to y3 minus our y2. So, having known this, we'll use this to develop the backward difference interpolation formula. So, I want to make my y0 the subject. Having known that nabla y1 is equal to y1 minus y0, I can say my y0 is equal to y1 minus nabla y1. What's common to them? Y1 is common. I can factor it out. I can get 1 minus nabla y1. I'll divide both sides by 1 minus nabla. Then I'll get my y1 is equal to y0 over 1 minus nabla. I can rewrite this as y1 equal to 1 minus nabla exponent negative 1 y0 using indices. I hope you get that. So this is our first equation. That our nabla y2 is equal to y2 minus y1. So I can make my y1 the subject. So my y1 will be equal to y2 minus nabla y2. So my y1, I'll factor out my y2 out. I'll get 1 minus nabla y2. So I want to make y2 the subject. So I'll divide both sides by 1 minus nabla. My y2 will be equal to y1 all over 1 minus nabla, which I can rewrite as y2 equal to 1 minus nabla exponent negative 1 y1. What is our y1? We find the y1 to be 1 minus y1 to be 1 minus nabla exponent negative 1 y0. So we substitute them to get our y2. So we can therefore say my y2 is equal to 1 minus nabla exponent negative 1. And in place of the y1, we substitute 1 minus nabla exponent negative 1 y0. So we can say our y2 is equal to 1 minus nabla. Add negative 1 to negative 1. Remember that is indices. That's negative 2 y0. I hope you are getting the clue. Also, remember we said that our delta y3 is equal to y3 minus y2. So we can say our y2 is equal to y3 minus delta y3. Please, let's check this as equation 2. So what do? We factor out y3 out. So we can say our y2 is equal to 1 minus delta y3. I hope you get that. We can make y3 the subject. So our y3 will be equal to y2 all over 1 minus, nabla, not delta, nabla. So we can rewrite this as 1 minus nabla exponent negative 1 y2. And what's our y2? Our y2 is 1 minus nabla exponent negative 2 y0. So we substitute there to get our y3 proper. So having known our y3 is equal to 1 minus delta exponent negative 1 y2, and we know our y2 to be this, we substitute. So we can say our y3 is equal to 1 minus nabla exponent negative 1, and in place of y2, we substitute 1 minus nabla exponent negative 2 y0. So we can say our y3 is equal to 1 minus nabla exponent negative 3 y0. So look at it. Our y1 is 1 minus nabla exponent negative 1 y0. Our y2 is 1 minus nabla exponent negative 2 y0. And our y3 is equal to 1 minus nabla exponent negative 3 y0. I hope you get the pattern that is developing. So you see the pattern is developing. So we can say therefore that our y4 will be 1 minus nabla exponent negative 4 y0. I hope you are getting it. If it is y5 will be equal to 1 minus nabla exponent negative 5 y0. Then we can say our yn will be equal to 1 minus nabla exponent negative n y0, which we can rewrite as yn is equal to y0 bracket 1 minus nabla exponent negative n. So having known that our yn is equal to y0 bracket 1 minus nabla exponent negative n, how do we expand 1 minus nabla exponent negative n? We are going to use this expansion again to expand that. That is to get the expansion for 1 minus nabla exponent negative n. So in this case, we can say that our x is equal to negative nabla if you compare. So x will be equal to negative nabla and our n is equal to negative n. So any place we see x, we substitute nabla, negative nabla, and any place we see n, we substitute negative n. Then we can say our 1 minus nabla exponent negative n will be equal to, so 1 in place of n, that will be minus nabla, in place of minus n, in place of x, negative nabla. I hope you get that. Then plus, in place of this n, negative n, in place of this n, negative n minus 1 over 2 factorial. Then in place of this x, negative nabla all square. I hope you are getting that. Then plus, in place of this n, negative n, in place of this n, negative n minus 1. Then in place of this n again, negative n minus our 2 all over 3 factorial. In place of x, negative nabla, so negative nabla exponent 3 plus in the other. Now let's polish this very well. So we can get 1 negative n times negative nabla. That will plus n nabla. I hope you get that. Then plus, when this multiply, or when we factor our negative out, it will affect this. That will become positive. So we can get n plus 1. I hope you get that. All over 2 factorial. Then negative nabla square will be positive nabla square. I hope you get that. Then let's do it again. So we can also get plus. When we factor out negative out here, it will affect this. That become positive. So we'll get n plus 1. When we factor out negative out here, we'll get n plus 2. Then we put the negative here. Then times negative nabla cube will be negative nabla cube will be negative nabla cube like this. I hope you get that. Then plus 3 dot all over 3 factorial. So this negative is positive. So this place will be positive. I hope you are getting the cube. Then we can get the expansion of this is equal to 1 plus n nabla plus n plus 1 over 2 factorial nabla square plus n plus 1 n plus 2 over 3 factorial. Since this is positive, we get nabla cube there, then plus 3. Then we can say the expansion of this is this. So having known that the expansion of this is this, we substitute this in this place. So now let's substitute. So we can say our yn will be equal to y0 bracket. In place of this, we substitute 1 plus n nabla plus n plus 1 over 2 factorial nabla square, n plus n plus 1 n plus 2 over 3 factorial nabla cube, then plus 3 dots. So we can expand. Our yn is therefore equal to y0 plus y0 plus n nabla y0, then plus n plus 1 over 2 factorial nabla square y naught, then plus n plus 1, n plus 2 over 3 factorial nabla cube y naught plus in that order. I hope you get that. This is called Gregory Newton's backward difference interpolation formula. I hope you get that. So the question is, does it mean that when we want to use Gregory Newton forward difference as well as backward difference in solving one particular question, are we going to construct two difference tables? No, we'll just construct one difference table. So I'll show you how to locate our y naught, nabla y naught, nabla square y naught in that order, and that for the delta 2. So we have been learning about the Gregory Newton's forward difference formula and backward difference formula. So with the forward difference formula, we say yn is equal to y naught plus n delta y naught plus n minus 1 over 2 factorial delta square y naught plus n minus 1 n minus 2 over 3 factorial delta cube y naught plus in that order. And the backward difference formula is yn is equal to y naught plus n nabla y naught plus n plus 1 over 2 factorial nabla square y naught plus n plus 1 n plus 2 over 3 factorial nabla cube y naught in that order. So the difference, however, is that whilst the forward difference is having negatives, so minus, 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 the backward difference is having positive, plus, plus, plus. Now, how do we get our y naught, delta y naught, delta square y naught, delta cube y naught? So how construct your difference table? This value here is y naught. The second difference, the first difference, delta y naught. The second difference, delta square y naught. The third difference, delta cube y naught. These are the leading differences. The leading differences. So you just use that formula to get your values. You just use these values and substitute into your formula to get what we are looking for. So the backward difference too. How do we get nabla y naught, nabla square y naught? So this becomes your y naught. If it is backward difference, this becomes your y naught. This becomes your nabla y naught. Then this becomes your nabla square y naught. Then this becomes your nabla cube y naught. So this is your y naught, nabla y naught, nabla square y naught, and nabla cube y naught. So if it is forward difference, you use this. If it is backward difference, you use that. I hope you get that. So that's how we do. Now, how do we determine the value of the n in the formula? I will indulge you to check out my videos on how to apply Gregory Newton's forward difference and backward difference in solving questions on YouTube. Until we meet again, please remember to subscribe to my YouTube channel. My name is Gregory Newton.